Okay, so in this video we're looking at the simple harmonic oscillator potential. So V is just proportional to x squared, so it's just like a spring kind of potential, like 1/2 kx squared. Only I've written it in terms of the angular frequency, so omega is like square root of k over m. And with this, our Hamiltonian becomes this expression. And so our differential equation, our eigenvector equation for the Hamiltonian becomes this. And with a little bit of rearranging, so if I want to kind of get phi prime prime by itself. So I just divide by minus hr squared over 2m, and then I just bring this factor over to the left and factor out some common terms. And so I can write my differential equation like this. And so this problem is more difficult than the ones we found before. This differential equation isn't easy to solve. And luckily, it's already been solved for us, so we don't actually have to do anything. Or rather, a similar kind of equation has been solved. So this equation is called the Hermite differential equation. And its solutions are known, so this in here is any integer or 0. So as long as n is 0, 1, 2, 3, and so on, then the solutions to this differential equation are known. And so this differential equation almost looks like the differential equation that we have. It's not quite there. So what we can do is just try to rewrite our equation as so that it looks like this equation. And then once we've done that, well, we know the solutions to this equation, so we'll know the solutions to our problem. And, obviously some math nerds already figured out how to do that. It's not too bad to do. All we have to do is introduce a new variable called y, which is just square root of m omega over h bar times x. And then because, we have this second derivative term here with respect to x, we want to rewrite that in terms of a second derivative with respect to y, which is easy to do. And so I just want to rewrite my equation in terms of y. So I'll get so d dx is square root of m omega over h bar times d dy. And because it's the second derivative, I get basically, this squared kind of. So I get an m omega over h bar here. And now phi prime prime means second derivative with respect to y. And then I can just plug in my, solve this for x and plug that into here. And so I'll get this. So now it's written in terms of y. And then I just want to resimplify it. So I'll just, again, get this phi prime prime term by itself. So I'll divide by m omega over h bar. And then I simplify a few things, but it's not too bad to get to this equation eventually. And so now we're here, and this differential equation is looking a lot closer to the Hermite differential equation. It's just missing this plus 1 here. So what I'll do is I'll just subtract 1 and add 1. And then it's basically there. All we have to do is identify this 2n with 2e over h bar omega minus 1. And if we do that, then our equation does reduce to the Hermite differential equation. And notice I said before that we know the solutions to this as long as n is any integer or 0. So that gives us a condition. It gives us the eigenvalues, basically. So this is our, it's what tells us the allowed values of energy and hence the eigenvalues. So E, from this equation, we get can be n plus 1/2 times h bar omega, where again, n can be 0, 1, 2, 3, and so on. So again, there are an infinite number of eigenfunctions, so an infinite number of solutions to this. And so what are the solutions to this? Well, they are the Hermite functions, which are basically, so for, the nth value of n, phi n of y is just proportional to these Hermite functions, which are basically a Gaussian times these things called the Hermite polynomials. So these, again, are just known functions that are polynomials. that you can just look up. But the point is we know them. So we can just write down these solutions here. And this is in terms of y, so we really want them in terms of x, which is easy to do because y is simply related to x. So phi of x will look like this. So again, we have this Gaussian term and our Hermite polynomials. And then this kind of ugly factor out in front is just the normalization factor. So this factor ensures that the modulus of the wave of these functions squared integrated from minus infinity to infinity is 1. So again, what we've done is we've plugged in our simple harmonic oscillator potential to our Hamiltonian, and then reduced our Hamiltonian eigenfunction equation to the Hermite differential equation, whose solutions are known. And once we've done that, we can just write down the known solutions of the Hermite differential equation and go back to our old variable and get our solutions that way. And along the way, we've also found the eigenvalues from the condition that the solutions to this equation are, there are only solutions to this equation when n is some integer or 0.